Raw cosine can confuse generous users with similar taste. Adjusted cosine corrects the rating baseline. You'll build an item-based collaborative filter with adjusted cosine that mean centers user ratings and returns drama with a supporting neighbor. I'm Professor Pi, teaching AI foundations with simple Python. Recommendation systems need to separate what people enjoy from how they score. One person gives nearly everything a 5. Another saves high ratings for true favorites. Item-based collaborative filtering finds items that receive similar reactions, then uses those item relationships to suggest something new. A movie with high raw ratings may not match a user's taste at all. What matters is whether viewers rated it above or below their own normal level. Adjusted cosine focuses on that personal reaction, not the raw number. We will use a small ratings table to uncover item relationships, then turn them into a recommendation for one user. The key idea is simple. Compare each rating to that user's usual rating before looking for shared taste. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need each person's normal rating level. This snippet uses NumPy's np.nanmean to reveal each user's personal rating baseline. Raw ratings mix preference with scoring habits, so a 5 from a generous user does not mean exactly what a 5 from a strict user means. The ratings array stores 5 users by 5 items, while np.nan marks items a user has not rated. np.nanmean ignores those gaps when building means, so missing ratings do not pull a user's baseline down. The printed user means show distinct baselines. Those baselines give us the reference needed to separate rating scale from taste in the next step. Now that every user has a baseline, we can compare 2 items without letting generous scoring dominate. This example uses NumPy's np.dot and np.linalg.norm to compute one adjusted cosine similarity. np.dot combines matching values into one shared score, while np.linalg.norm measures the size of each set of values. Subtracting means from ratings creates centered, where positive values mean above a user's norm, and negative values mean below it. Add cos keeps only users who rated both items, then compares their centered columns and guards against a zero denominator. The same rows can represent customers rating products. The printed adjusted cosine shows jazz and rock have a strong positive relationship after personal rating habits are removed. One pair is useful evidence, but a recommender needs to compare every item against every other item. This code builds a full NumPy similarity matrix and ranks the nearest items to puzzle. Looking at one pair is not enough for recommendation, because every candidate needs a comparable relationship score. np.I starts self-similarity at 1, which gives each item a perfect match with itself before the real pairwise values are added. adj-cos fills each item pair symmetrically, so the relationship from puzzle to drama matches the relationship from drama to puzzle. np.argsort orders the puzzle row from strongest to weakest. Removing puzzle itself leaves drama and racing, so the visible neighbors confirm that the adjusted similarity matrix can support item selection. For more practical lessons across Python, data, and AI, you can subscribe and keep building these ideas with me. Those neighbors are promising, but we still need to turn them into ratings for items the target user has not seen. This snippet uses NumPy's np.where to find unseen items and score them from rated neighbors. Adjusted cosine becomes useful only when neighbor relationships are translated back into the target user's rating scale. Score selects the k-set to 2 highest similarity rated items, weights their centered deviations with np.dot, divides by the absolute weight total, and adds means user. That last addition matters, because the result returns to the user's usual scoring range. Increasing k blends more rated neighbors and may smooth a score. Decreasing it concentrates on the closest evidence. The printed unseen scores compares racing and drama on the same user-specific scale, preparing a final ranked recommendation. We have predicted scores now, so the last step should select the best item and show the evidence behind it. This example uses NumPy's np.argmax and np.argsort to return one explainable recommendation. A score alone is hard to trust, so the final step keeps both the winning item and the neighbors that influenced it. np.argmax selects the highest value from score, while np.where hides unrated candidates before np.argsort retrieves the two rated neighbors for y. The printed top item identifies drama, reports its predicted score, and exposes puzzle and rock with signed similarities so viewers can inspect the evidence. A positive similarity means the neighbor supported drama through a similar pattern of above or below average rating. A negative relationship would act as counter-evidence instead. When a catalog has many stable items and users rate only a small fraction, item-based filtering is often a practical choice because item relationships can be reused across many recommendations. But sparse overlap still matters. If two items have only a tiny shared audience, their similarity can be noisy. Real systems often require a minimum number of shared raters. Then blend this method with popularity or content features for items that have little rating history. This small example shows the full path from raw ratings to drama. Find each user's baseline, compare items through centered reactions, score unseen choices, and reveal the neighbors behind the winner. Adjusted cosine does not erase personal taste. It makes that taste easier to compare fairly. Try changing the number of neighbors and watch how the unseen scores change. Then, inspect whether the supporting items still make sense for the recommendation. What practical recommendation topic would you like to explore next, such as cold starts, ranking, or evaluation? Subscribe if you want more clear Python and AI lessons.